Thank you very much for the kind introduction. I'm very happy to be here. This is indeed my first time in Brazil and also my first time to participate in one of these major international conferences. Today I would like to talk on numerical studies of recovery chances for a simplified EIT problem. This is in fact work I conducted with my colleague Roman Unger and under supervision of my supervisor Ben Hofmann. In the following, I'd first like to start with a brief motivation for our model, our approach. Then I would like to introduce or reintroduce the general EIT model, continue with our simplification, and conclude the talk with numerical examples and conclusions. First of all, what is EIT? As we've heard before, it is a minimal invasive technology. The idea is to apply current, or for most applications, it is desirable to apply current to the boundary of a specimen. And then, therefore, afterwards measure voltages or potential differences. And the idea is to then reconstruct the electric conductivity within that specimen. For practical applications, especially in medical imaging, it is, again, desirable to apply current and measure voltages. The focus on these, or most applications, is usually to detect inclusions. For example, we've seen Bastian's thorax before, where we have some sort of different background conductivity and some inclusion we're looking for. The example displayed here is actually from an engineering background. So here you have a specimen, a hole is drilled, and they're looking with some sort of method or algorithm for that inclusion. Then our approach is actually fundamentally different. So there's these newly developed or newly developing materials, CNTs, carbon nanotubes or carbon nanofibers. And the engineers can derive some sort of connection between mechanical strain within these materials and electric conductivity. However, in our approach, we have this specimen, but we don't know if we have some sort of background conductivity. Because what they do is they have a round specimen, which we'll see on the next slide, and then they bend it. But there might be stress on it already, and we don't know if there's a background conductivity. This motivates our approach, which we can see here, some sort of stripe or strip structure. So we take the round sample, bend it, and therefore we get the structure. Again, we'll see that slide later on to talk about electrodes and the modeling of those. So let me reintroduce the general EIT model. We have some sort of omega in R2, smooth boundary, a conductivity function sigma of x within omega, as well as the electric potential U. And then the autonormal derivative can be, or autonormal derivative over the boundary can be interpreted as current. And we then further know that the Laplace equation holds within the interior of this omega. So the Neumann to Dirichlet map is defined by this lambda. It maps current measurements onto voltage measurements, and G denotes these Neumann boundary data. UG is the weak solution of the Laplace equation we've seen on the last slide. Again, this is the current on the boundary. A few conventions, as introduced by Bastian before, these diamond spaces are introduced or commonly used in the literature to overcome non-uniqueness of this Neumann boundary problem. And this is L infinity with a positivity constraint. So these conductivity functions have to live in this space. So the forward operator, or one set of measurement, is given by this A. We have a conductivity function, which we map onto the Neumann to Dirichlet map. So that is the forward problem. And the inverse problem is we have this Neumann to Dirichlet map, and we try to recover this conductivity within omega. So our simplification. For obvious reasons, in practice, it is impossible to get full boundary data because we always have to use some sort of measurement device, electrodes, and there are lots of theoretical results for full boundary data, but this is impossible. Therefore, we have K electrodes on the boundary. I and Q denote the current and voltage, respectively, on that electrode. And we further assume steady state, so the in and outgoing currents add up to 0. It is then assumed that the conductivity sigma is isotropic. So electrode modeling. There are numerous electrode models used, and they're described in the literature. One of the most common is the shunt electrode model. It says that there's no current outside the electrodes. Also, the current on every electrode is equally distributed, and the overall current is then the integral over that electrode. It is further assumed that the potential is constant on every electrode, therefore the name shunt model. In the discretized situation, this leads to the following situation. We take K measurements on K electrodes, map them, or then, we add current on K, or a subset of these electrodes, and then we measure voltages on the remaining. And this is just the discretized form of the operator A previously introduced. Again, for our simulations, I'd like to talk later on. What did we do? We took this sample omega, discretized it with a triangular mesh, which we later used for the FEM calculations to solve the Laplace equation. We got 32 boundary edges, and K is 8, so 8 electrodes, which is very limited data. Then again, we set 2 Neumann boundary conditions. So this is, we apply current on one electrode, and we the current is injected on one and leaves the specimen on another one. They're neighboring electrodes, although not adjacent, obviously. To overcome the non-uniqueness of the Neumann problems, we set a further Dirichlet boundary conditions on one arbitrary electrode. So we then have this sample, we rotate the electrodes to get further measurements. Again, as we can see here, these are the Neumann boundary conditions where we add current. We take measurements on the red electrodes as well. This is our Dirichlet boundary conditions. Then again, just to clarify this, we've talked about voltages and potentials. What's the difference for those who are not from the field? Actually, we're measuring, or a voltage is a potential difference. So in this case, we're not actually just measuring voltages here, but the potential difference between those two electrodes, just to clarify this. In our model situations, we get a full set of measurements. So we have one conductivity vector with n dimensions. This is the number of stripes or strips used in the examples. We then take a set of measurements, solve the PDE, and get a solution of it. Therefore, we rotate the electrodes again, solve the PDE with the FEM method, and our model or operator F is then an 8 times 8 matrix. Again, just to clarify this, every column of F is then one set of measurements before we rotate it. This is the implementation or numerical implementation. So the next step is to use a least squares approach. So assuming that we have a true conductivity vector sigma star given, we try to find or minimize this discrepancy norm and try to find sigma with some sort of admissible solutions Q that minimizes this this least squares problem. Delta or F of delta, F delta is some sort of noisy data with a noise level delta. This is additive noise in this case. So we take the exact forward operator and perturb it with some sort of error matrix epsilon. So the entries of epsilon are normally distributed, IID, with some form of variance delta squared or d squared. This d squared is chosen in such a way so that the expected value of the squared relative error is delta squared, which leads to this value for d. So to continue, we did the first example was to use just 2 different conductivities. Why? We assume that the whole situation is, or we know the whole situation is severely ill-posed, and we assume that the this forward operator F is actually injective, and therefore we took the very simple example with just 2 conductivities. So we've got one conductivity here, another one here. We calculated all forward operations for admissible solutions in Q with a sufficiently large discretization. In this case, it was about 50. And what can we see on this slide? This shows us the discrepancy norm of that functional. And on the right-hand side, you'll see the corresponding level set. So even if we have just two conductivities, our assumption is that the larger one is very difficult to recover, whereas the smaller one is very easy, no problem. On the other hand, if they are very close to each other, the level sets become nearly concentric circles, such as this, with a different sigma star. And it's very difficult, these are all noiseless, by the way, to recover either of those. So the next step was to increase the discretization. We used n is 5 with more stripes or more strips. And again, we did loads and loads of forward calculations. And our assumption was that F is not injective. And we have seen that very, very different conductivity vector sigma might lead to the same measurement. So the norm between the two of those is very small. As you can see here, totally different values. So our assumption was, again, that this F is injective. This, again, led us to further investigate this. And this slide shows the linear interpolation between, or even extrapolation here, between two sigma vectors, sigma star and sigma 3. The norm is, between the two of those, is very small. So I interpolated between the two of those and extrapolated here. This is noiseless, and there's 5% noise on this figure. Yeah, what we assumed was there would be a additional local minima here somewhere, which is not the case. To further investigate this situational behavior, we looked into level sets of these functions. Obviously, we can't show pictures of 5-dimensional level sets, so we kept 3 components fixed, looked at the remaining 2 with some sort of sigma star given here, and the 4th, the 5th, and the 1st component are fixed, and the 2nd and 3rd you can see here. This is noiseless, and this is with added noise of 10%. So what we assumed again was that there would be a local minima here or here, which is then not the case. Given we have not found any local minima so far, we used a algorithmic least squares approach. So we used the Liebenberg-Marquardt algorithm to find these, or to minimize this least squares problem for admissible solutions in Q. And this sigma delta opt denotes then this found solutions. On the following slides, the examples are calculated with some sigma star here and some starting value. Obviously, we've done plenty of those, and this is just one example, one realization. Again, let me stress this. For the previous examples, we calculated all forward operations in this set of Q with a discretization of about 30. And this is like a tremendous forward operation. I mean, we have to solve literally millions of FEM problems, and it takes a very long time. So we used about 100 simultaneous threads on about 12 workstations, and it took about 2 weeks to get all these results. So there's no linearization, it's just forward operations via FEM solutions. Also, if you try to employ this particular approach or any algorithmic approach, for every step we have to calculate an approximate Jacobian. So that requires, in turn, n, if our discretization is n times the forward operator. Each is a couple of sets of measurements, so it takes a long time. So in order to speed this up, we used multilinear interpolation in places that are not on this mesh which we pre-calculated. So what can we see on this slide? In the first column, we have the mean value noise level. Then there's one particular realization. The third one shows us the reconstruction error. The fourth is the mean error to noise ratio and the random error to noise ratio. So the most important numbers are these. We can see that the mean error to noise ratio as well as the random error to noise ratio, even for very high noise, is constant. So the problem might not be as ill-posed considering these small discretizations as we first believed. in order to further investigate this behavior, we looked at the conditions numbers of the approximate Jacobian. Then we looked at the single values and the condition numbers for some sigma star. And what can we see here? We used various conductivity vectors with a different structure. So these are constant, some rising values, and some alternating sinoid sigma functions. Again, we scaled them and we can see that even with them a scaling, there's no change in condition number, and they're all very well conditioned. So to end the talk, I'd like to draw a few conclusions from this. So our numerical studies lead to the following assertions or assertions and conclusions. This whole problem is not as opposed as we believed. This discrepancy norm has, in fact, no local minima, or we don't think it has. And the least squares approach indeed has a global minimum, and therefore we can justify algorithmic approaches. Also, in these small dimensions or with these small discretizations, regularization by discretization takes place, and there was no need for further regularization methods or stabilization methods. So with a few references, I'd like to end this talk, and thank you for your attention.